Hey there, chemistry team. You ready for video number 2 on our solids and solubility series? For us, again, that's chapter 18. Depends what textbook you're using and what edition of that textbook you're using. Here we go. Remember, 2 types of solubility problems we're going to work at. Either given solubility, solve for KSP. There's your fastball. Or given the KSP, look it up on a table, solve for solubility. There's your curveball. Boom! Only 2 kinds. That's you're facing a pitcher with only 2 kinds of pitches. So when I'm coaching right now, it's pretty much, a fastball and a changeup. I've coached softball, I coach baseball, little league, and both. Most of the kids just have fastballs, but every once in a while you get a changeup going on, you can really mess them up. So you want to prepare them for the changeup. So let's start with the fastball, then we'll do the changeup. Here we go. Let's say we've got some zinc carbonate solid. We want to know what its KSP is. Now, it's on our KSP table. We know what the answer is ahead of time. I wouldn't do that on a test. I wouldn't give you a KSP value to look up. Right? But we can say, hey, either maybe in lab we measured its solubility, or maybe we looked that up in a table in the Handbook of Chemistry and Physics. You probably Googled it. All right, so let's say the solubility is 1.12 times 10 to the minus 4 grams per liter. That's pretty small. That's really, really small. The temperature is irrelevant here. Let's just say it's 25 degrees Celsius. The temperature has no impact whatsoever on our particular problem unless we did the same problem at a different temperature. Let's say it was 35 degrees Celsius. That solubility would go up. That value would go up. But that's not important at this point. How are we going to attack this problem? All right. Well, let's take a look. First thing I'm going to do if I'm stuck on a test, my brain, I can't remember, just write an equilibrium equation, right? And then do an ice table, set up an equilibrium expression. That should be routine for you. You don't even know what you're doing yet. And then we'll figure out what the heck to do, all right? Is it a type 1, type 2, or type 3 problem? So let's set up our equilibrium equation. So we've got zinc carbonate, right? So let's get our zinc carbonate solid. That's going to dissolve, right? So the water molecules are going to pull the cations and anions out. So we're going to get the zinc ion, which hopefully you know is a +2. Zinc and cadmium, right? I think they're both always a +2. If you don't know that, hopefully you know the charge on the carbonate's a -2, and they're a 1-to-1 ratio. Charge won't impact the answer on our problem, but we should know that by now, right? And since there's a subscript of 1, we get 1 here, and there's only 1 carbonate, so we get 1 carbonate over here. So 1 mole of zinc carbonate solid will produce 1 mole of zinc ions and 1 mole of carbonate ions in equilibrium, because those can recombine and reform the solid. So we get the reversible arrows. Sweet! And we don't know the KSP, right? So let's put KSP equals question mark. I don't know. We got to figure that out. That right there tells you that's that first kind of problem. We do know the solubility though. All right, let's set up our ice table. Here we go with our ice table. Let's do our ICE, and let's figure out if this is a type 2 or type 3 problem. Move this over, bring this down. You can make the ice tables as beautiful or ugly as you want. Doesn't matter to me. We don't have to worry about the solid, right? Nice. Any solids and liquids, you just black those out. Or in this case, purple it out. So we have, now, didn't give you any information at all on the initial concentration, so we're assuming 0, right? So we're assuming 0 of those. Is it pretty obvious this is going to have to shift right? If we're starting with all solid and we have no product, it's got to go right, so Q is 0. So let's do this in this color. So Q equals 0, which is less than KSP. And so that's going to shift to the right. Which really doesn't matter because we have no reactants to worry about. Remember, the solid concentrations assumed to be so high, it doesn't matter how much you lose. I mean, it's just a tiny little bit. So the amount you lose is always going to be equal to the, so the equilibrium amount is always going to be equal to the initial amount. We don't have to worry about it. So we are going to form X of the zinc ions and form X of the carbonate because we've got coefficients of 1 in front of both. Think about solids, though. If we had something that had like 3 of the cations for 1 of the anions, we'd end up having 3X here. So you can get some pretty crazy calculations later. This is a pretty simplistic one. I'll increase the difficulty level for the next one where we're not going to get x and x. So I might get a 3x and an x, or a 5x and an x or something. So 0 plus x is x. 0 plus x is x. You got to love these easy ice tables, right? There we go. Now, from the ice table, we can set up the equilibrium expression, correct? We know the equilibrium expression. But let's think about this problem here. Do we know x? Now, I don't know KSP, so I cannot do a type 3 equilibrium problem. That's impossible, right? Because I would need the KSP to solve for x. I can't do it. So there must be some information. This is a type 2 equilibrium problem. There's something in the problem that must allow me to calculate x, all right? So let's see. What did I give you? Temperature is irrelevant, the solubility. So somehow from the solubility, so this is 1.12 times 10 minus 4th grams of zinc carbonate per liter of solution in this case, assuming that, the volume, if we have 1 liter of water, you add the solid, it stays at 1 liter, right? So we're assuming that's liter of the solution. Let's do that. Let's set that up and see if we can't convert that grams to moles of zinc carbonate. And once we have moles of zinc carbonate per liter, can we go from moles of zinc carbonate to moles of zinc or carbonate? Doesn't matter. Find one that's x. So you look at the two of them. If one of them say 4x and the other's x, go to the x. We're trying to figure out what x is, right? So if I go from the grams of zinc carbonate to moles of zinc carbonate, then I can go 1 mole of zinc carbonate to 1 mole of zinc. I'll have moles of zinc per liter solution. That's x. The solubility gives us x. That allows us to determine x. That's why this is a type 2 problem. I give you a hint on the equilibrium concentration of something. I obviously have no room left on my board, so I want you to pause it, and I will pause it myself and erase this board, but take the solubility in grams of zinc carbonate per liter solution, convert that to moles of zinc ion per liter of solution. That's x. Set up your equilibrium expression, plug in the value of x. You got your KSP, man. Have fun. Do it, do it, do it. All right, let's see if you got what I got. Depends on what periodic table you use as well, right? Some periodic tables go out, stop at 2 decimal places. Some stop at 1. Some go to 5 or 6. Whatever one you're using is fine. We're going to get probably at the end the same answer. Maybe not out to the non-significant digits, but to the proper number of sig figs, we should probably get the same unless you're really rounding off your atomic masses per se. But if you're in my class, just use the periodic table I have on my website. We're good to go. Here we go. Let's take our solubility of 1.12 times 10 to the minus 4 grams of zinc carbonate per liter solution. That's what that means, right? That liter to the -1 means it's in the bottom. Let's divide by the molar mass. So I got from if you use my periodic table, right? I just hunted down numbers from all over the place. So my zinc is 65.382. That's changed a little bit over the years. My carbon is 12.011. I've seen some with 12.0108. I'll change that some year. Oxygen 15.9994. That's the German one, right? 15.9994. So take 15.9994 times 3 plus 12.011 plus 65.382, limited by fewest decimal places, which would be 3. I get 125.39120, good to 3 decimal places, grams of zinc carbonate per mole of zinc carbonate. So just dividing by the molar mass. And then you can see from the chemical formula, 1 mole of zinc carbonate produces 1 mole of zinc plus 2. You can see that here, right? The 1-to-1 mole ratio. So if you calculate that out, we got 6 significant figures in the molar mass, 3 significant figures in the solubility. The mole-to-mole ratio is exact, so I'm going to be good to 3 significant figures. So that would be 8.9320 times 10 to the minus 7th moles of zinc ion per liter solution, which is molarity. Right? And that's good to 3 significant figures. Well, if you look at your ice table, that's the concentration of zinc ion. That's equal to the concentration of the carbonate ion. They're the same, which are both designated as X at equilibrium on your ice table. Oh, all right, because this was X and this was X. So I rewrote the equilibrium equation up on the board just so we could do our equilibrium expression. Let's pop it out. KSP will be equal to the equilibrium concentration of zinc, which was defined as X, times the equilibrium concentration of the carbonate ion from the ice table is X, if you look back. So that will just be equal to X squared. But from the solubility, we know what X is. It's 8.9320 times 10 to minus 7. So let's plug that in. So let's take 8.93 vertical dash line, 20 times 10 to the minus 7. And we don't need to worry about the units, right? Because we're calculating K values. Although we are using molarities, right? So the final answer we're going to get is a concentration-based equilibrium constant, the KSP with a superscript C. And remember, if we compare this to the tables in your appendix, those are typically your thermodynamic-based equilibrium constant. So that'll be a KSP with a superscript T, even though it's not showing there. So there's a good chance our value will be slightly different from it. And if I remember, activities are always lower than molarities, is that right? So let's compare what we get as a concentration-based one versus what is shown in the table and see if we're smaller or higher and see if that makes sense, knowing that activities are always smaller than molarities, right? Because that activity coefficient is always less than 1. All right, let's square that. I'm going to pause it for 1 second because I'm about to sneeze. Woo, feeling better now. You ever have a sneeze just come out of nowhere and you're like, oh, I just paused that in time. I almost went just pow all over my computer screen. That would have been bad, but some of you would have thought that pretty funny. All right, let's square this baby. If you crack yourself up, you'll live longer. All right, here we go. So KSP, I got 7.97 vertical dash line. 80 times 10 to the minus 13th. That's pretty small. So that's going to round up to 7.98 times 10 to the minus 13th. Not a really tough problem, right? And this again is our KSP with a C up there because we use molarity. So let's look up zinc carbonate just out of curiosity. I don't know the value. Zinc carbonate, let's look it up with a thermodynamic-based one. You know, there's some experimental error in the solubility calculations as well. So let's find zinc. Do we have zinc carbonate? There's zinc carbonate right there. Zinc carbonate, 1.4 times 10 to the minus 11. All right. So we got a value quite different from that using the molarities. So taking a look, you know, activities, we don't know the activity coefficients. So if we had done this, if we knew the activity coefficients, and we're able to multiply those by the molarities and get the actual activities and solve for this, we probably get a closer value to that. But you can see using molarities creates a bit of an error, and then measuring that solubility, there's probably some experimental error in the laboratory experimental procedure. Hopefully not too much. All right, I'm going to pause this. Let's do the second type of problem where we will know the KSP value from the table or from the problem. We're going to solve for the solubility. So it's just the reverse of this, just backwards. You ready, gang, for the second kind of problem? Here comes your change up. All right. Let's say we got some bismuth 3 iodide, right? BiI3 solid. Now this one you'll see is for ours, we don't have it on our KSP table. So this is one I might give you on the test. So either I give you the KSP, so bismuth 3 iodide or bismuth iodide there. 7.7 times 10 minus 19. That's the KSP. It's either going to be on the KSP table. If you don't see it on the KSP table, it's got to be in the problem. If you don't see that, raise your hand on an exam, right? And I forgot to give it to you. What is its solubility, right? Either you're given the solubility, solve for KSP, given the KSP, solve for solubility. Here we go. Set for, now I didn't give you any information on any equilibrium concentration. So this is a type 3 problem. Let's set up our equilibrium equation. Set up our ice table, figure out which way it shifts, set up our KSP expression. Let's have at it, gang. You ready? Let's do it. Let's take my solid, BiI3. So that's going to break apart into 1 bismuth plus 3 ion. And then see that subscript of 3 on the iodide? That's going to give me 3 of the iodide. So that's going to change this problem a little bit in our ice table because we're going to get 3x over there. Let's set up the ice table. Boom. Again, this can be as pretty or as ugly as you'd like. Doesn't matter to me. Segment it out. ICE. This should be, you could probably do this faster than I can while I'm doing it live. That'd be pretty cool if you did. Just whip that out. And hopefully you don't talk as much as I do. Let's do this in red. Obviously, we don't worry about the solid, so we'll just blot that one out. I didn't give you any information, so we're assuming we are starting with 0 of all of those to start with. Just solid. So this has to shift right. Q is 0, right? So Q equals 0, which is less than KSP. So it's going to shift right. Most of the time it's going to shift right. But you got to watch out. Every once in a while, somebody might throw a wrench at it and have it shift to the left, and all the negatives become positive, positives become negative. We don't have to worry about this, right? So this is a coefficient of 1, so we're going to be forming X of that. How much of the solid dissolves is how much, X amount of the solid is going to dissolve, so that will be X, how much bismuth ion you get. But we're going to get 3 times that amount of iodide, right? Because it's a 3-to-1 ratio. So the I minus will be positive 3X for the change. So at equilibrium, bismuth will be the initial plus the change. 0 plus X or just X. The iodide will be the initial 0 plus the change 3X or just 3X. So the only difference is the 3X here versus the other problem. Let's set up our equilibrium expression. So KSP. Let's see, that's going to be the bismuth cation concentration raised to the power of 1 times the iodide concentration raised to the power of 3. This is where things get fun. Raised to the power of 3. All right, we're going to plug 3x raised to the power of 3. So we're going to get a 3 cubed term in here. We don't have to notice there's no initial minus x here. Right? That's what makes solids different than acids and bases. We don't have an initial amount minus x. So we don't have to make any assumptions here. We just plug it in. It's pretty nice. No quadratics, no assumptions, no tricky math, nothing like that. So bismuth will be x, right? Iodide will be 3x, but I have to cube that whole term, right? So if I simplify this, what's 3 cubed? 3 times 3 is 9. 9 times 3 is 27. So 3 cubed is 27. So that's x times 27x cubed. Everybody see that? Let's break this up. So that's x times 27x cubed. I normally don't show that step. So this will be 27x to the 4th. Ho, ho, ho. A lot of people forget to cube the 3. And so they're off by a factor. They do the problem right, but they don't get the 27. They just leave it as a 3x to the 4th. It's 3 cubed, which is 27, right? Ha, 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 ha. Now, all we have to do is we know KSP, right? So I've run out of room on my board. So you go ahead and do it. Take 7.7 times 10 to the minus 19 equals 27x to the 4th. Solve for x. X is the molar solubility of the bismuth ion. Can you go 1 mole of bismuth ion to 1 mole of the bismuth iodide precipitate? That gives you the molar solubility. Then multiply by the molar mass. That'll give you grams of BiI3 solid per liter solution. There's your solubility. Now, I said grams per liter, but we don't need that. If I say solubility, we're assuming grams per liter. If I wanted molar solubility, I would have said that. See if you can finish this problem. I'm going to erase the board and pop it up there for you, and we're done with this video. All right, did you get it? Did you get it? Did you get it? Let's pop this in. So I'll just rearrange this. So x to the 4th will be 7.7 times 10 to the minus 19th over 27. So KSP is this. Move the 20, divide both sides by 27, right? And what are we going to get here? So x will be 7.7 times 10 to the minus 19th divided by 27 to the 1/4 power raised to the 0.25, your little caret symbol to the 0.25. Two significant, that 27 is exact, so we get the 7.7 to 2 sig figs. I get 1.2 vertical dash line, 99 times 10 to the minus fifth, and that'll be molarity. I'm going to pause and let my kitty cat in. Hold on. All right, kitty cat's happy now. He's meowing at the door. Loud cat. That was my three-legged fat diabetic cat, Tubby. If you're stuck here, I'm going to erase the molarity there and write it out at what it actually is. Look at the ice table. X is the bismuth ion concentration, right? So if I, instead of writing molarity there, if I write moles of the bismuth ion per liter of solution, hopefully that will give you a hint on that we can take this down, convert moles of the bismuth ion to moles of the solid, and then multiply by the molar mass of the solid, and we're good to go. So the solubility, let's bring that number down, 1.299, whoops, I forgot my dash line there, 1.299 times 10 to the minus fifth moles of the bismuth 3 ion per liter solution, all right? That technically, if I ask for molar solubility, all we have to do is convert this to moles of the solid, and we got the molar solubility. We don't need the molar mass. That's boring, though. So let's convert this. 1 mole of bismuth ion was produced from 1 mole of the solid. Right? If you look at the equilibrium equation, they're in a 1-to-1 mole ratio. The iodide ion was a 3-to-1 mole ratio. So I tried to find that one that just has a value of X. Makes life easier. So that's going to cancel out the moles of the bismuth ion. Now let's use the molar mass. Let's multiply by the molar mass of the bismuth iodide solid. So we got 3 iodides. On my periodic table, my iodide is, what is that? 126.90447. Who got so many decimal places there? Right, so that's 5 decimal places. Bismuth is right here. That is 208.9804, good to 4 decimal places. So take the iodide times 3, add the bismuth, and we're good to 4 decimal places based on that. Oh, where'd my pen go? So let me squish this in here. So for every mole of bismuth iodide solid, I got a solubility of 5, big number, because iodine's pretty heavy, right? So I got 589.6938. There's my 4 decimal places, 693810 grams. Now I ran out of room on my board there. Happens a lot in regular lecture too. But I got the double screen in my big lecture hall. I only got one board here. That's all I can fit. So 589.693810, good to 4 decimal places. Won't really matter though. I mean, it's way more. We're limited to 2 sig figs anyway here, so we got a truckload. Molar masses very, very rarely limit your significant digits. And then the moles of BiI3 cancel out. So we've got grams of the solid per liter solution. We got, that's the units of solubility. Yay! So I get to 2 significant digits, 7.6, vertical dash line, 60. That's a weird looking 0, times 10 to the negative 3rd grams per liter. Right, grams of solid per liter solution. That's going to round up to 7.7 times 10 to the minus 3rd grams per liter. Or if you want, you could go grams times liters to the negative 1 power. There's your change up, right? Fastball, solve for given solubility, solve for KSP, change up, given KSP, solve for solubility. That's it. They're just reverse of each other, and they're pretty straightforward equations. Okay, next few videos, we're going to ramp it up a little bit and look what happens with the common ion effect, right? How does that change solubility if you throw a common ion in there? We're going to look at the salt effect, right? What if you throw some potassium nitrate solution in there and look at that salt effect and how that impacts it? And then we'll look at whether some solids have susceptibility to acid, right? If the anion of the solid is basic in nature, we can destroy it or reduce its solubility by adding some acid. Oh, you can see what's coming. Enjoy!